Um, so I have to preface this talk with quite a few remarks. The first remark being that I'm probably not telling anything new to the teams that are actually have been working on category theoretical problems for the entire week, because it's Wednesday now and you probably have like encountered everything that I will present here. That's one thing. The other thing being that I only contributed minuscule amounts of content to the category theory library, and yeah, it's actually maintained by a whole list of people. I think that's all that are listed on the website, at least. Yeah, among them being Barvik, who's here. I'm not a maintainer. Yeah, so when in doubt, maybe even ask those people instead of me. So my knowledge is like restricted to those parts of the category theory library that I actually use. Yeah. Okay, so that being out of the way, I decided to call the first whole section of this talk challenges. Well, because it's yeah, I guess it's important to state that category theory is, for several reasons, one of the most challenging fields to formalize, and I will list a few reasons for why that is the case. So one reason is that it's one of the few cases where we actually need dependent types. So we've not talked a lot about the foundations of Lean being dependent types, and we've not seen too many dependent types. In some branches of MathLib, you don't encounter them at all. You just encounter predicates. So the only dependency that you have dependencies are really in propositions, but not in types. And this is a case where you really you get your nose really pressed on the fact that you have to deal with type dependencies, and you could do without them, but then you're much more in a world of pain than actually using dependent types. So assume that we wanted to define the notion of a category and didn't have dependent types. Then the only way to do that would be that, okay, it's a structure and we have a type of objects, but then we would have like just a type of morphisms. So just first like an unstructured pool of morphisms, and then afterwards of saying, okay, we have a field that contains the morphism, you would then say, okay, yeah, well, we need functions that tell us the domain and the codomain for each morphism. And so these would be functions from more to obj. And then, for example, the identity would be a function from obj to more. So far, so good. But then you need a whole bunch of equalities. You need that the domain of the identity is x. You need that the codomain of the identity at x is x. And that's only for the identity. So if you wanted to write the composition, you would have like something of obj, yeah, of more to more to more. But then you've not captured the fact that composition is not global, but it's partial, because you need to take care of the fact that you only can compose morphisms where the codomain of the first one actually coincides with the domain of the second one. And so, yeah, you won't be happy if you do it that way. And that's why you really need dependent types. So something like this. Instead of having just a type of morphisms, an unstructured type, you have a type family. So you have, for all two objects, you have a type of morphisms. And that's yeah, that's something that in other branches of mathematics you don't really need. Yeah.
So it's like type questions that you don't answer from this level. But if you wanted to make this first approach to become precise, like how would you do the flow to add this condition? Right now, I mean, it's not really of type more to more to more, right? Because that would be global function.
Yeah, you could. You could say that for all f and g in more, where we have that if if codomain of f equals domain of g, then we have something more.
But you could also define the follow function and then put extra fields to specify on.
Yeah, you could do something like we did with the division, where the division is always 0. The division by 0 is always 0. So we have a global operation, even though you actually want it to be partial. But that's also like a very dirty solution. Yeah, I mean, in this case especially. So, and see, in the dependently typed version, you will just be able to write identity for each object. It's a morphism from X to X. So instead of having these 3 lines, you just encapsulate it in this 1 line. And so the composition would be that for all, to do these, put these in implicit, as implicit arguments for all X, Y, and Z in obj. You'd have function from morphism of X, Y to morphism of Y, Z to morphism of X, Z. Yeah, and that's everything dealt with. Well, that being said, there's lots of places where the dependencies actually pose a problem, especially for tactics, because sometimes you want to prove that 2 morphisms are the same, but then hidden inside one of these implicit arguments, you have that the codomain or the domain of the morphism has like a slightly different shape, and that the tactic won't work, and all these kinds of things. I won't go into the details of that, but yeah, you might have already encountered these problems when you've worked with the category theory library. So that's one issue. The next issue is that you've probably already seen universe parameters. We've never really explicitly introduced the hierarchy of universes, but I think through one way or the other, it's probably been like making its way to your knowledge that we don't have like just one universe of types, but yeah, we have a universe prop of proposition, and then we have a universe type of types, and then we have type 1, which is the universe that contains type, and type 2 and type 3 ad infinitum. And actually, category theory is one of the fields where we actually need that infinite hierarchy, because it's one of the fields that actually deals with having something like a category of categories. And so the more nesting you want to have, the higher the universe level of your definition has to be. And so we need categories to be universe polymorphic. And if we want to make it fully general, they have to be doubly universe polymorphic, because there's one universe level, which is the universe level of the objects, and another universe level that's the universe level of the morphisms. And so the definition category, I should actually like control and click on it. This is the definition of the category. Okay, it's a bit, it's not in one place because it actually encapsulates the data in another structure. But you can see that it actually it depends on a type of object, and then okay, it generalizes the notion of a quiver, and yeah, the quiver is the thing that provides the type family of morphisms which go into the sort V. So you have one parameter U for the objects and one parameter V for the morphisms. Yeah, and so you need to carry around all these universes, and if you have a functor, if you have the notion of a functor between 2 categories, you already have 4 different universes. If you have limits where the diagram is in a certain category of already 4 universes, so yeah, it's inevitable that you will at some point more or less like drown in different universes, and you better make yourself comfortable with that. Then the next challenge is a completely different one, is that in many category theory books, associativity is mostly considered as being strict. We don't usually even put parentheses around morphisms, and it's one of the, it's a bit like in algebra. It's one of the places where associativity and the unit laws are just considered a given. So their proofs in books will be much easier than having them actually in Lean. Though this is a part where actually the automation in Lean, like ASOP, for example, or the simplifier, can actually help us a lot. Yes. The next challenge is that our formalization has to be general enough that it can deal with the fact that category theory makes a lot of use of canonical objects or canonical constructions of many sorts. So we will be talking about like for example, the limit of a certain functor, when in the end you will construct a functor again which is isomorphic, and then you take the limit. And in literature you will assume that those limits might be the same on the nose, while actually they're just uniquely isomorphic and not exactly the same. And so you have to deal with those issues. So the solution to this is to not, for example, to not make use of any sort of equality between objects and categories, but always state things in terms of isomorphism, which is good practice anyway when you're doing category theory. But it's even more vital in formalization. That's okay. That's the next point. And that's already the challenges that you face when just doing normal category theory. Well, all these challenges obviously grow exponentially when you try to do a higher category theory in the same way. So we do have the notion of bicategories in MathLib, but that's as far as we can go in MathLib right now. And that's the one group that works on the definition of quasi-categories. But that definition then will be in terms of simplicial sets and not in terms of a structure that looks like that. A structure that looks like that will be easier to use, but it's also it's impossible to have something. We don't have structures with infinitely many fields. So it's kind of, not sure if it's proven, but it's not possible to extend this kind of dependently typed way of objects and morphisms all the way to infinity, because we just can't do that in the theoretical setting. Okay, and one last challenging point is that universal mapping properties are not actually properties in Lean, because they contain the selection of an object, of morphisms, and then uniqueness in form of proof. So many things which are considered proofs in literature are actually definitions in MathLib, because they are just that. They are just a selection of an object with certain properties. So much for the challenges. Let's look at. I already looked at the definition of category. So it's a type class, and it's an unbundled type class, which means that we have a type, which is then the type of object, and the type class adds the type of morphism and all the other necessary data and all the category laws. And so you have a symbol for morphisms, which looks almost the same as the normal function symbol. In some fonts, it looks slightly longer. In some fonts, it looks exactly the same. And we have this symbol for a composition in the category theory library, which looks entirely different than the circular symbol for the composition of functions, which is a good thing because the entire category theory library actually, thankfully, uses diagrammatic order instead of function application order, which I think, yeah, is a really good decision because most category theorists I know think in diagrammatic order. So for example, you could express in an arbitrary category something like this, like F being a morphism from X to Y, composed with the identity, that's our symbol for the identity, composed with G, equals F composed with G. Obviously, that's a really simple lemma. And then, for example, for every category, we might want to define a functor. So this is the symbol for functors from the category to type, where the objects are just functions. Like, okay, we have one object, so this is basically the hom, the hom category. So the functions, the objects are morphisms from X to Y, and and the thing I wanted to show with this one was that if you look at the definition of a functor, okay, it extends a prefunctor again, but you will see that, and I think we haven't seen that in the other talks, the declaration of the fields of the structure actually end with a colon equals by something, which means that Lean will automatically try to solve these fields of the structure with this tactic. And ASOP-cat is a modification or a configuration of ASOP which is made to be tailored to solve small trivial goals in category theory. And so the fact that a certain functor to be preserves the identity and the fact that it preserves composition is always tried to be solved automatically by ASOP. And so we won't even have to state it explicitly. So if we hadn't done that, we would have to give the proof that it preserves identity, for example. But since ASOP-cat can do this, we don't even have to state that line, and that makes us, for example, instantiate some really easy functor. That also holds true for forgetful functors, and everything where the functor reality is not some really complicated proof, but basically follows trivially, can be filled in automatically by Lean. Yeah.
So this double arrow is a functor in general?
Yeah.
So is type given the structure of the category as well?
Yes, it has a canonical. There's a category of types where the objects are types and the morphisms are functions. So it replaces the category set for almost all intents and purposes. And
Yes, I basically the same question. So Lean can always not recognize when type is just the type of types and it's the category of types. It's not the same thing.
Well, that's just a feature of the type class system in general. That's just when you say real, then actually it's just the type of real numbers. But with the type class system, it will always deduce a canonical ring structure for the reals, and likewise, it will always deduce the canonical category structure on type.
If you make that into the definition and gave you the name and you would check, you would see a coercion somewhere. Because this type is.
I don't think so. No. We could do like synth. How does it work? First the
Category
type. Okay, it's called types. It's a large category. Yeah, and that's the point where you see that comp fg is defined as being G composed with F. And that's pretty much the only category where the associativity and the identity laws hold really strictly, because G composed with F composed with H really associates strictly within Lean. But yeah, that's just as a side remark.
So what's the relation between type and types?
Like the small types was just the name of the instance. Usually when we define instance, we don't even give them a name, and Lean will fill in the name of the instance automatically, but we don't really make sure that the instance names are actually nice, because they're hidden by default. And actually the instance names in the category theory library are one of the most horrible things of Mathlib, because they tend to grow really big, and they actually clutter the auto completion of the HTML online documentation of Mathlib really badly. So yeah, that's something that needs to be cleaned up in the future, I guess. Okay. Yeah, one big topic for category theory is obviously limits. Okay, I talked about the universes. So we have the definition is limit, which takes as a parameter a cone of F. So it basically just states, okay, an arbitrary cone over a functor is a limit. Does that by having the map down to the other point of the cone, to the other cone, the triangles that make up the rest of the cone, and then the uniqueness of the map. So that's just the notion for a certain functor for a certain cone to be a limit, and then we have has limit, which says, okay, yeah, a certain functor has a limit, and then we have a whole chain of slight generalization of that. Is, for example, you have like a very certain, very concrete sort of diagram. For example, you have has binary products, which is the property for a category to have like all binary products, which then that's basically concretization of has limits of shape, which is a more general more general notion, which states that all functors with a certain domain are equipped with limits. And so we also have has finite limits, which is the obvious thing, and then sometimes it's important to state. So there's something called has limits of size, and the size here doesn't really talk about the cardinality of the diagram, but instead it talks about the universe of the diagram. And there's cases where we really need to specify that a certain category only can provably provide limits up to a certain diagram universe. And then there's a standard notion of has limits, which then fixes the universe of the diagram to be the same as its home sets. And it turns out that in practice, that's most of the times that's what we want. Yeah, and then there's also something like called limit cone. There's something called get limit cone, which then selects by choice. I think that's the reason why I mentioned this on the basics section on Monday, which chooses a limit cone for us. And most of the time, theories in category theory library are formulated in a way so that they work with arbitrary limit cones. But obviously, there's many of them. They're just all uniquely isomorphic. But there's also, using the axiom of choice, there's a way to select one limit cone. And actually, that's the thing that makes it possible to say, okay, we have something like in the theory of binary products, for example, this has a limit, and so we can actually we can actually select it. So we can actually say, okay, we can choose by the axiom of choice, we can choose one arbitrary limit cone or co-limit cone, and so for example, we can use notation like this to refer to this specifically chosen limit.
So if you do this in the category types, do you then, I mean, this choice here seems to be any choice in the category types, but rather want to be the type x times y. Is this somehow?
Well, yeah, I think the only thing you get is a priori a type that is isomorphic, so to say, and that's just an equivalent type to, yeah. So yeah, that's basically the downside of using the axiom of choice, that you don't get these. Yeah, that's also a point where in the literature nobody cares about whether it's the right choice or whether it's a different choice from the one that you actually want.
I mean, there is this. I was thinking there's this notion of, what was it called? I mean, this default element of a type.
Yeah, that's for non-empty types.
Exactly.
Yeah.
I mean, could one somehow say? Okay, I was thinking
that it should always. Yeah, it's tough, but yeah, but it's not done. I think if you choose something by the axiom of choice, the only thing that you can say about it is the one property that it should. Yeah. So yeah, that's about like something like binary products. You can imagine that the same holds true for every sort of of limit. And then I wanted to give a small insight into what kind of useful tactics we have. So there's one tactic which is called slice. So you see in the goal view that associativity is implicitly bracketed to the right. Since here in the file we've actually bracketed it explicitly, and then the brackets disappear here, and also you see the hovering. And so oftentimes we want to rewrite something, or we want to change a small portion of like a huge chain composition of morphisms, and now we have to like rewrite along the associativity axiom quite a lot of times in bigger terms. I mean, this is a really small example, and then so if we know, okay, we want to focus on the, for example, second till the third morphism in that chain, we could do something like slice LHS 2, 3, and then it will automatically reassociate the left-hand side and present us with these with this new goal, where now the turnstile has turned into a pipe, and we can now use like a limited set of tactics to modify that bit of the actual goal. So for example, we could rewrite along our hypothesis E, which says that F composed with G equals G prime. And so after we've done that, now we've replaced F composed with G by G prime without needing to explicitly reassociate the left-hand side. Yeah, now to close the goal, we could like apply ASOC one last time, which just reassociates the right-hand side. And the tactic ASOP-cat that I've mentioned is used to automatically fill in fields of the common structures in category theory. Actually does all these things by itself. So for example, instead, you could have just done ASOP-cat here, and it automatically does the reassociation and so on and so forth. So yeah, I think the co-end project group can confirm that it actually does do a stunning amount of work by itself without actually needing any further configuration or anything. Then also to the topic of reassociating. there's a feature which is called re-assoc off. And what it does is it gives us for any statement or for any lemma like this, let's take I composed with F equals I composed with G. It will give us a reassociated version of that statement. So for example, here we have something like I composed with F composed with H, and we want to reassociate that. We want to rewrite along this this E, and we see that on the left-hand side, also the associativity is in the wrong way. And what reassoc does is, so for every lemma that has some sort of equality, or for every statement that has some equality, whether it be a lemma or like a local statement, it generalizes it to by putting an arbitrary morphism on the left-hand side and on the right-hand side by the end of it. And that actually allows us to rewrite along this lemma or along the statement, even if the bracketing is wrong. Yeah, and the more complicated the terms get when you're dealing with equalities of morphisms, the more important this stuff becomes. There's also like an attribute which is called add reassoc that you can add it to your definitions, and it will automatically generate a reassociated version of your lemma, also with this arbitrary H added to the right of it. Yes?
Several things you are saying seem to have the same problem for any associative thing. So is there something like a plus or anything? A composition of normal functions?
So I think the reassoc thing would be useful for the entirety of Mathlib. So far, it's only been used by the category theory library, but I'm not actually sure why that is. I think it would make rewriting faster in the whole of Mathlib, and especially also in the algebra section of Mathlib. And yeah, so I think it should be applied everywhere. Because it's like the reassoc thing is a really smooth thing because it's quick. It doesn't need to search for the right association, but instead it's just deriving a more general version of the same theorem. Yeah. So and then there's a tactic which is called element-wise. I won't go too deeply into it. Many of the categories we are dealing with are actually instances of something called concrete category, which is just that. It's just a category together with a forgetful functor that goes to type. So that's everything where the objects have some sort of carrier, like groups or rings or whatever. And the tactic element-wise and the attribute element-wise is basically like reassoc for any theorem that we give to Lean. It automatically derives a theorem which, instead of being on the on the level of objects, is on the level of elements. So yeah, what's a good example? Yeah, I don't know. For example, in the category of types itself, it would be that. No, I mean it's all trivial in the category of types. But yeah, it's very useful if you if you're dealing with any sort of concrete category. Okay, so much for the tooling. Yeah, just a short, like I'm not taking a tour through all of the source files because they look pretty frightening. So just a list of the stuff that we already have. So there's limits of all sorts of shapes and sizes, and they're all in category theory.limits.shapes. So that's the folder they're in. We have adjunctions, we have monads, we have adjoint functor theorems. We have the Yoneda embedding and the Yoneda lemma. So the Yoneda embedding is this. Yeah, it's a functor from C to C op to type. Yeah, we have the proof that it's full. We have the proof that it's faithful. And what's maybe important if you're looking for certain categories is that the categories that, yes?
When you said adjoint boundary theorem, what should we think of? Like, this is like a presentable and limits and has adjoint.
Yeah, that sort of stuff.
So the theory of accessible and presentable categories also.
I mean, I don't know. I mean, also the stuff that yeah, functors preserving limits have a, no, I don't have to get it wrong, have a left adjoint and so on and so forth. Oh, yeah.
There's not accessible or presentable categories, but we do have the generalizable function theory and specializable function.
The solutions of conditional.
Yes.
What we also have, what I think it's important for like the more modest category theory formalizations is stuff like the construction of all finite limits from products and equalizers. That's also there. Yeah, what I wanted to say, the category instantiations for algebraic structures are not in category theory, not in the folder category theory, but they are in algebra.category. There you find, for example, group cat. So why can't we just use group? It's because group is what we call unbundled. Group takes as an argument its carrier, and then is a type class that just adds the group structure to the carrier. But for categories, we obviously want to talk about not all group structures on a given set, but we want to talk about all groups. And so we need to bundle the carrier together with its group structure. And if we look at the definition of group cat, we see that it's just defined as bundled group. And if we look at the definition of bundled, it's this. So it's a structure that contains an alpha, which is just the carrier, and a structure which just it's just some type class on that carrier. I mean, this is very general, but you can think of it as a general vehicle to take a carrier, take an arbitrary type class on that carrier, and bundle it together in one type. And this is then used to define something like group cat and automatically derives coercions from an object in group cat to the carrier to make the distinction between the object, between an object of group cat and its carrier a bit smoother. Yes, we have a bit of cohomology of chain complexes, but I don't really know how much. We have enriched categories, abelian categories, monoidal categories, and triangulated categories. And yeah, for everything else, you best just search in the Mathlib docs and see if you can find anything. In general, I'd have to say it's probably not the biggest category theory library that exists. And maybe it's one of the fields where there's other theorem provers that actually have a more extensive library. Yes?
Do you have some examples of such?
Of what?
Of theorem provers which have a more extensive library?
I mean, for very specific stuff, I'd say that even Acta has a bigger library, and then there's also the Unimath project, which has lots of category theory in a univalent setting. Yeah. Okay, so that's as much as I want to say. There's a few exercises in this lean file. If you work on those exercises and get stuck, don't wait too long to hit me up and give you hints, because I'm not sure they're easy, and yeah, you might need some help. Yeah, so thanks for listening. Any questions? Yeah.
So you said that categories are doubly polymorphic. Is this really necessary, or could one just have said, let's take the maximum of U and V always?
I mean, what do you mean by max? So if you have the maximum of two things, it's already doubly polymorphic.
Yeah,
but
no, I mean, could one have just defined in the definition category just use one universe and later?
Yeah, then there's some categories where for example, where the universe of the objects can become arbitrarily large, but the morphisms are still super simple.
Okay, so you're right.
So,
I mean, I was thinking if you want to do some infinity categories, you probably say let's not just.
yeah. So I don't remember the motivation, but big parts of the category theory library was just had a single polymorphism, and especially the limits weren't fully universal polymorphic. And I had a formalization project last year where I noticed this, and that formalization project basically turned into a session of over a few weeks trying to refactor the whole category theory library to be compatible to actually accept this case. And it's, yeah.
And another small question, so you showed lots of limit stuff. I mean, do they corresponding co-limit things?
Oh, yes. Yeah, I completely forgot about that. So we have, in an earlier session, we saw that we have a nice way of automatically deriving stuff for additively written groups if you have the multiplicative version. Unfortunately, we don't have that for deriving the dual stuff. So we have lots of boilerplate code. So if you look at, I don't know, if you look at isLimit, I mean, obviously you see, because of this little bar, you see, okay, I don't have any, this is 1,000 lines. You see that, so you will see every little definition is repeated twice, once in its dual version, and yeah, it's probably not a good state, and it should probably be automatically generated. So far, it's not, and yeah, somebody would have to take up that that exercise of writing a lean extension that does that automatically. Yes.
So I don't know very much about universities, but I'm wondering if you ever run into like science issues. For example, is there a universe that contains type n for all n?
No. I'm not sure if you ever run into such issues. I think you can engineer a problem where you would run into such issues, and there's other theorem provers that actually have something called type omega. But so far, I think nobody has really complained about it. and I would suspect that the core developers of Lean would be very hesitant to actually change the core foundations of Lean just because of a few category theorists. Yes.
So these bundle categories, do they automatically get full function to cap or something?
To type, yeah. Yeah. So. No. Oh no! I mean, no, they don't. Not sure if it always has to be a functor. That's the thing. Yeah, bundled is bundled. You can bundle everything, even if the forgetful functor is not actually functorial, I guess. Yeah.
Well, I guess it's not even a functor in the sense of him, right? Because the unbundled version is not a.
Yeah, but the thing that projects out the carrier, like for example, for groups, it, yeah, and for groups, obviously, it's functorial, and for most other examples, you can think of it as well. Yeah.
I have some vague memory that in Lean 3, there was an instance of that being functor actually. To category types, it was functor. I wondered.
Yeah. So, but the bundled field is really that's all the file there is. There's no functor in here. Yeah. Okay.